Thank you for listening to this Defense Energy Seminar. Today's topic is quantum security for microgrids. I am Peng Zhang from Stony Brook University. My research area is in power systems, microgrids, and cybersecurity. I'm directing Stony Brook University's Power System Lab. So the strategic directions of my lab include AI-enabled resilient power grid operations and quantum engineered resilient grids. Other than that, we also work on microgrids, network microgrids, software-defined smart grid, grid resilience, and grid forming technologies. Microgrids are promising new paradigm for electricity resilience. A microgrid is an autonomous local power grid formed by a collection of power loads, distribution energy resources, and coordinated control. It can flexibly host renewables and energy resources and operate continuously even without utility supply. Further, if multiple microgrids are interconnected and well controlled, those network microgrids offer much more resilience benefits and can even help the main grids to quickly restore power. Communication has always been crucial in microgrids for maintaining reliable operations and achieving resilience benefits. With the increasing deployment of renewable energy resources, information technologies, and real-time automation and control systems, its importance will only grow. Currently, data transmission security in power systems relies on cryptographic systems that use keys to encrypt and decrypt messages. These keys are generated by classical public key systems such as Diffie-Hellman DH and Rivest-Shamir Adleman RSA. The security of these systems depends on the difficulty of solving certain mathematical problems, like the discrete logarithm problem or the factoring problem. While modern computers cannot efficiently solve these problems at this point, they are vulnerable to attacks from quantum computers. This is why we need quantum security. So in this talk, we'll briefly talk about a few topics. First, we'll briefly talk about the basic ideas of quantum communication. Then we'll talk about how to use quantum communication to secure a single microgrid. And then we'll talk about quantum secured network microgrids. Let's talk about the basics of quantum communication. Quantum communication uses quantum bits or qubits to transfer information. So a qubit is represented by the spin of an electron or the polarization of a photon. Unlike a binary bit, which has to be in either 1 or 0, a qubit can be a superposition of both states, 0 or 1. So for the quantum communication we're discussing, the polarization of the photon will be used to achieve qubits. Two bases, namely horizontal polarization or Z basis, and diagonal polarization or X basis will be utilized. If a source and its receiver operate on the same basis, the information can be well received. However, if different bases are used, the information received will be uncorrelated with the transmitted information. So now let's talk about quantum key distribution. To defend the attacks initiated by quantum computers, we will need to use quantum cryptography. QKD is the most mature and well-known example of quantum cryptography. A QKD system uses qubits to generate and distribute keys for two parties. It basically consists of quantum channel and a classical one. The quantum channel is used to transmit qubits from one party to the other to generate a raw key. The classical channel is used to conduct post-processing to establish the final keys. With the final keys, data messages can be encrypted and later decrypted over the classical channel. The unique property is that measuring an unknown qubit will change that state, and then the two parties can both detect the occurrence of an eavesdropper who is trying to gain knowledge of the keys. Therefore, the generated quantum keys are theoretically secure. To better understand how quantum keys are generated, let's look at an example. There are many QKD protocols, such as BB84 decoy state, seek state, etc. The principle of the BB84 protocol is shown in this figure. There are two communication parties, assuming them to be Alice and Bob. First, Alice randomly selects a binary bit from 0 and 1 with certain probabilities. She also randomly selects a basis from the two bases, namely horizontal, vertical, and diagonal, with certain probabilities. Then Alice used the select basis to encode the selected bit into a qubit. For example, if the binary bit Alice selected is 0 and the basis is horizontal, vertical, the qubit Alice prepared is the 1 shown on the left-hand side. Then Alice sends this qubit to Bob through a quantum channel. When Bob receives this qubit, he randomly selects a basis from Z and X and uses the select basis to measure the received qubit. If the basis Bob selects is the same with the one Alice selects, Alice and Bob will share the same result, and otherwise they will have different results. For example, the first row in the figures represents the binary bits Alice selected. The second row represents the basis she selected. The third row represents a basis Bob selected. Note that all these values are random. For the first qubit, the bit Alice selected is 1, and the basis is diagonal. The basis Bob selected is horizontal. Because they selected different bases, Bob will not get the same result Alice prepares, and this result will be discarded. For the second qubit, the bit Alice selected is 1, and the basis she selected is horizontal. The basis Bob selected is also horizontal. Because they select the same basis, they will have the same result, and this result will be kept there. So finally, there will be a series of raw qubits. After raw qubits are generated, the two parties, Alice and Bob, use a classical channel to conduct a number of actions, include error correction, privacy amplification, etc., to establish the final keys that are theoretically secure. Okay, next, I will present how we integrate quantum key distribution into a single microgrid. Here is the quantum secure microgrid architecture we devised. Within a microgrid, there's a control center which receives data packets from different loads, DERs, here DER means distributed energy resources, and sends control signals to certain DERs or loads. As building a QKD system is very expensive, we only establish QKD systems for those critical communications, such as the ones between the control center and local controllers. For example, a typical PQ control is considered in this work, where the real and reactive power references are sent from the control center through quantum channels. The load management is sent from the loads to the control center through classical communication, as they are not critical. Because QKD itself is vulnerable to noises and attacks, we develop a key pool sharing strategy to improve the system resilience. The basic idea is that when one key pool lacks keys, a certain number of key bits will be shared from a neighboring key pool. So let's briefly introduce the quantum secured microgrid testing environment. So here we implement the QKD system into a real-time digital simulator environment, RTDS environment. The microgrid model is developed and compiled in a software called ArcCAD, and then runs inside the RTDS hardware. The microgrid control center, MGCC, is running in a remote server. It can receive data from and send data to the RTDS hardware through the campus network. The quantum algorithm runs inside the control center. It generates quantum keys continuously and stores them into a key pool. When there's a data message sent from the microgrid or RTDS by the remote sender, a certain number of key bits are consumed, and proper control signals are sent from the control center to the RTDS. In this way, we integrate the quantum key generation and key consumption. Here, the quantum key generation speed is determined by the quantum algorithm, and the key consumption is determined by the real data transmission between microgrids, here is RTDS, and the control center. Now let's introduce the microgrid model we used for this test. So as you can see, this figure shows the hardware connection and the operation of the control center. A typical microgrid system is used to evaluate the performance of QKD-enabled quantum-secured microgrid. So the buses within the microgrid are rated at 13.2 kV, and the microgrid is connected to the 138 kV main grid through a transformer and circuit breaker. So the microgrid can operate in island mode or in grid connect mode. The DERs in this microgrid include a 5.5 MVA diesel generator, a 1.74 megawatts of PV system, and a 2 megawatts doubly fed induction generator wind turbine system. The diesel generator uses the droop control to regulate the microgrid frequency in island operation and to provide real and direct powers in both grid-connected and island modes. Both the PV system and the wind turbine use a maximum power point tracking system to maximize their power output. 3 switched capacitors are connected on bus 1 to facilitate voltage synchronization in the microgrid. A lithium-ion battery storage is further connected on bus 2 to provide a backup power and store extra energy when the microgrid is in islanded operation. The battery model consists of 250 stacks connecting in parallel, and each stack having 250 cells in series. A PQ control is designed to regulate the output power of the battery, and how much powers of the battery should be generated are determined by the real and direct power references transferred from the MGCC via a communication channel. Let me briefly explain how the QKD-based microgrid communication network works. On the MGCC side, the server initially enters listening mode when the system is running. At this stage, the server is receiving any network packet whose destination IP and port match those of the server, respectively. Once a packet arrives, a quantum key with the same length of the received data is extracted from the key pool, and the corresponding control signals are generated. The server then enters a sending mode and starts to send out control signals to the target DERs. After finished sending the control signals, the server or the MGCC returns to the listening mode. With this testbed, we perform several tests on the QKD performance. Here's the first case where we test the impact of data transmission speed. We use Wireshark to monitor traffic between RTDS and the control center. The larger data transmission speed, the sooner the key will be consumed. The data transmission speed has a large impact on the QKD-based microgrid. When the fiber length L between the MGCC and the local controller is set to 50 kilometers, and each data packet consists of 64 binary bits, a speed larger than 20 packets per second will lead to the exhaustion of key bits in the key pool. Also, we can see that the larger the data transmission speed, the sooner the quantum generated keys will be consumed. For a speed of 40 packets per second, the exhaustion lasts around 100 seconds within the key generation period. This long shortage can cause serious damage to the microgrid operations, as there's no key in the key pool for encryption and authentication of data messages. We also evaluated the performance of the system under different scenarios. This case illustrates the performance of microgrid before and after communications start working during the grid connected mode. So at the first 3 seconds, communication is disabled. The balance of the total power generation and the sum of loads is achieved mainly by the main grids. When the communication is enabled at t equals 3 seconds, storage starts to respond to the changing loads, and power balance can be well achieved. Similar results can be observed in the second figure on the right-hand side, where the microgrid switches from grid connect mode to the islanded mode. As you can see, with the quantum communication system, the system is well balanced after 3 seconds of operation. A QKD system may pose severe impact on the microgrid operation, because especially when the keys generated by the QKD system are exhausted. So in this case, we evaluate this potential impact. From this figure, you can see the microgrid performance when the keys are exhausted after the 3-second operation. It can be seen that the system eventually collapses after 18 seconds at time t equals 21 seconds. So in this case, the delay caused by the QKD is 1 second. It can be seen that because this 1 second delay added to the channel, the storage updates every 1 second, and because of that, the output of the diesel generator varies significantly. And in fact, we also tried different delays caused by QKD. As you can see, the larger the delay is, the more unstable the system will be. Actually, in another case, when the delay becomes as large as 3 seconds, it directly leads to collapse of the microgrids during the island mode. In this case, an evaluation of key generation speed and the different fiber lengths L and noise level E is provided. The noise can be either from ambient environment or caused by a cyber attack. A strong attack on the quantum optical environment will result in large E. The real-time simulation results are given in this figure, where L is set from 1 kilometer to 80 kilometers. E is set from 5 by 10 to minus 4 to 9 times 10 to minus 4, with a step of 10 to minus 4. And each packet consists of 64 binary bits. As you can see from the test result, a small L shows grid performance over a large L under the same noise level, which means that when we implement QKD in microgrids, ideally, microgrid control center and the local controller should be close to each other to achieve a better QKD performance. The key generation speed is sufficient with small L and a small noise level, but this performance deteriorates drastically when the noise level increases, which means that we need to be very careful about potential cyber attack so that the performance of the key generation can be guaranteed. Those test results also give us valuable insights about how to choose the right data transmission speed. So only the data transmission speed is lower than some level, the quantum qubits will not be easily exhausted during the operation. Previously, we talked about the k-pole sharing strategies. So now, in this case, we studied the system performance with and without KPS. So without k-pole sharing, as we can see, there's a shortage of the qubits in k-pole number 1. For instance, at time t equals 17.56 seconds, the qubits in k-pole number 1 are used up, and the shortage lasts around 10.5 seconds until a certain number of qubits are generated again. Meanwhile, we can see that the qubits in k-pole number 2 do not have shortage issues in this case. And now let's equip the k-pole sharing to the microgrid system. After the KPS is activated, the shortage issues of k-pole number 1 are well addressed. Similarly, as you can see, at time t equals about 17 seconds, the number of qubits in k-pole number 1 is below the threshold, and immediately 20,000 qubits are added from the neighboring k-pole number 2. But this does not affect the normal operations of k-pole number 2, as the minimum number of qubits in k-pole number 2 is still above the threshold after sharing. In the last test case, we use a testbed to compare the performance of 2 different QKD protocols, namely the 2 decoy state protocol versus the 1 decoy state protocol. Specifically, k-pole number 1 stores qubits generated by the 2 decoy state protocol, and k-pole number 2 stores those qubits generated by the 1 decoy state protocol. Here, the fiber length is set at 5 kilometers, 7 kilometers, and 10 kilometers respectively. So the comparison results tells us that the one decoy state particle is more sensitive to the fiber length than the two decoy state particle. It only outperforms the two decoy state particle when the fiber length is very small. This is reasonable because the one decoy state particle is more efficient in that there are no vacuum decoys. However, due to the lack of vacuum decoys, it's more sensitive to noise and loss. Next, we're going to briefly introduce how can we equip QKD for network microgrids. And this figure well documented, how a quantum secured network microgrid architecture will look like. As you can see in this figure, the quantum channels are used within each microgrid between the microgrid center and some critical DERs. Meanwhile, the communication between the different microgrids have quantum channels to support the resilient operations between each other. As we discussed before, kpole sharing are often needed because it's very easy to run out qubits within the kpoles. So for network microgrid operations, we devise a two-level kpole sharing TLKPS strategy. So if you look at the network microgrids, if there are intermediate kpoles between the kpoles within microgrids, then we can easily transfer and share the qubits between microgrids. And this is the so-called the first level of TLKPS strategy. And if there's no intermediate kpoles between two microgrids, we use a different way. We use a post-quantum way. So basically, one of the microgrids with actual qubits, we can convert that qubits into a plain text and use that as part of the final keys to be used by the neighboring microgrids who does not have too many qubits left. So in this case, we can still enhance cybersecurity by indirectly share the qubits to the neighboring microgrid who needs more qubits. So this is called the second level of TLKPS. Once again, we set up a test bed to test the quantum secured network microgrid systems. It's very similar to the test environment for the single microgrid test. The only thing is that we implement more quantum channels, we deploy more kpoles. There are kpoles within microgrids, there are kpoles between microgrids to allow the two-level kpole sharing strategy to be tested. So in this test case, we established a test environment including 3 microgrids. As you can see, within each microgrid, there are microgrid control centers. There include their local kpoles. And between the 3 microgrids, there are some shared kpoles between each other. This is a one-line diagram of this network microgrid system. It has 3 microgrids, microgrid A, microgrid B, and microgrid C. In total, there are 2 diesel generators within the 3 microgrids. There are 2 large PV systems and a 2 megawatts of wind turbine system. So there are also 2 lithium-ion battery storage systems deployed in this microgrid system. First, let's illustrate how cyber attacks will impact network microgrid operations. As you can see from this test case, the attackers was able to easily break in using quantum computers. And after the cyber attackers intrude into the system, they change the control signals from the MGCC to the local controller. So in this case, actually, they change the real power reference of the PQ control for the battery from 0 to -6 megawatts. By doing this, within 16 seconds, they were able to collapse the entire network microgrid system. So those figures shows the voltage decreases and the frequency deviations and the system collapse. So after about less than 1 minute. The subplot C shows that when we deploy QKD, it's impossible for cyber attackers to break into the system. So they are not able to break the encryption or authentication process. So because of that, as you can see, the system performance is always in the normal range. Then we did some tests to show the effectiveness of this two-level capo sharing strategy. In this test case, we deploy some strong attack between microgrid A and microgrid C by introducing very high noise level in the quantum channel. We also deploy some weak attacks for other microgrids. And then we monitor the QKD system performance. As we can see, without having the two-level capo sharing strategy, there's soon a shortage of qubits in the shared capo KPAC. And with the two-level capo sharing strategy, the shortage issues of KPAC are well addressed. As you can see, another capo, KPAB, is able to transfer some qubits to make the KPAC always running normally above the threshold. Let's briefly talk about the future work in this direction. Currently, we are planning for three different topics along this direction. First, we plan to perform the experimental demonstration of QKD in microgrids. As you can see from the previous studies, most of the QKD systems are based on the QKD simulator. So now, currently, we are trying to establish the real QKD hardware based on the optical systems. And we're connecting this real QKD hardware with the RTDS simulator and trying to demonstrate and verify its effectiveness to defend different type of cyber attacks. The second direction is to adopt and derive new QKD protocols to make the QKD system lightweight, more efficient, and easy to deploy for microgrids. The third one is we are integrating software-defined networking technology with QKD systems so that we're able to scale the QKD system up to support the operation of very large-scale network microgrid systems and even for bulk power system operations. That's it. Thank you very much.